Hello everyone, welcome to my YouTube channel Physics Learning. Today we are going to discuss about BSc 5th semester Quantum Mechanics Unit 1 topic, Planck's hypothesis and Planck's radiation law. So let's begin our discussion. At first we will know what Max Planck says. Max Planck says that the spectrum got through black body by Rayleigh jeans. To explain this, he put up the theory of electric oscillator, but he failed to explain this. He says that inside a black body there is an electric oscillator, but inside this how the vibration takes place he could not able to clearly explain about it. So Max Planck took the step forward and found an empirical formula in the year 1900 to explain the distribution of energy in the spectrum of black body, and in order to deduce that formula he made some assumptions which we will discuss here, which may be called as Planck's hypothesis. So now the first assumption says that suppose this is a black body. Suppose this is a black body where radiations occur, and this chamber is not only filled with radiation but also filled with simple harmonic resonator, and this resonator vibrate with a fixed frequency mu. Again, when this resonator or oscillator come in contact with the gas molecules present inside this chamber, they exchange energy. And the resonator will become responsible for emission of energy. So here it is written, a black body radiation chamber is filled up not only with radiation but also simple harmonic oscillator or resonator, also called as Planck's oscillator or resonator, which can vibrate with all possible frequencies. When this oscillator come in contact with gas molecule, they exchange energy. So the oscillators called resonators are responsible for emission of energy. Again, the energy which is minimum, which Planck called as energy quanta. Quanta means group. Because this minimum energy is in the form of small packet. Now if we take out the total energy of that oscillator or that resonator, then we have the integral multiple of this minimum energy. So if we denote total energy to be E, so we know that E is directly proportional to mu. So we can write as E is equal to h nu, or E is equal to nh nu, where h is the Planck's constant. And n is equal to any positive integer. Now the energy is integral multiple. So according to Planck, this energy is no longer continuous. Rather it is discrete. And according to Planck, we know that E is equal to h nu. So the same thing written here, there is a minimum energy E called energy quanta and energy of oscillator are the integral multiple of this minimum energy. Thus, energy is no longer continuous but discrete. And the minimum energy E is related with the frequency of the oscillator and is given by E is equal to h nu, where h is the Planck's constant and h has a fixed value which is 6.626 into 10 to the power minus 34 joule second. Also, if n is the number of resonator per unit volume and EV is the total, E nu is the total energy or energy density, then the average energy of a Planck's oscillator is given by E bar is equal to E nu divided by n, where n is the number of resonator per unit volume, E bar is the average energy of a Planck's oscillator and E nu is the total energy, or we can say energy density. So we no need to derive. So in BSc the expression is not needed. The only thing we have to remember is the expression, which we get directly. E nu d nu is equal to 8 pi h v nu cube divided by c cube into d nu divided by e to the power h nu divided by kt minus 1, where k is the Boltzmann constant. K is the Boltzmann constant. So this is known as the Planck's radiation law expression. Derivation is not needed in BSc because it is not from the examination point of view, but yes, the expression you have to remember. Now, if we want to express the Planck's radiation law, which we got here, Planck's radiation law in terms of wavelength. This is in terms of frequency, but now if we want to find in terms of wavelength, then Planck's radiation law in terms of wavelength. So we can write the energy density E lambda d lambda belonging to the range d lambda can be obtained by using the relation which we know, one of the famous relation, mu is equal to c by lambda, where c is the speed of light, lambda is the wavelength and mu is the frequency. This one is the energy density E lambda d lambda belonging to the range d lambda. So now if we differentiate d mu with respect to d lambda, now if we differentiate d nu with respect to d lambda, then we get d nu by d lambda is equal to d by d lambda c by lambda. Since here c is constant, so it will come outside, d by d lambda 1 by lambda. So we will get minus c lambda to the power minus 2. We are applying here one of the expression we know, d by dx of x to the power n is equal to n x to the power n minus 1. This formula we already know, we are applying here. I am writing here directly. So we can write d nu is equal to minus c divided by lambda square d lambda. So in order to remove this negative sign, we have to give modulus. So d nu modulus is equal to minus c by lambda square d lambda. Now, as we have got the expression earlier, this expression we write here, E nu d nu is equal to 8 pi h nu cube divided by c cube into d nu e to the power h nu by kt minus 1. So, as we are doing in terms of wavelength, so E lambda d lambda is equal to 8 pi h c cube lambda cube 1 divided by h by lambda kt minus 1 c divided by lambda square d lambda. We are simply substituting the value of mu is equal to c by lambda here and here, and here, and also d nu, the value of d nu substituting here. So we are getting the final expression while cancelling this, 8 pi hc lambda to the power 5 into d lambda e to the power hc by lambda kt minus 1. E lambda d lambda is equal to, so this is the final expression in terms of wavelength. So in our next lecture we will discuss about Planck's formula for lower frequency and higher frequency. Till then, if you have any doubt regarding this topic, you can please comment. You can comment me below, and if you like the video, then please share and subscribe. Thank you.